Hello everyone. Today I would like to talk about direction of arrival estimation and array antenna beamforming with a mutual coupling. I am Qiaowei YUAN from Tohoku Institute of Technology, Sendai, Japan. This is the contents of my today's talk. Firstly, I would like to introduce myself and then talk about the research background, and then would like to focus to explain what is the universal steering vector, and then we'll show you some estimation results obtained by universal steering vector. And finally, I would like to show you some results about adaptive beamforming of array antenna with mutual coupling. Now I would like to introduce myself. I'm professor and also head of IoT Research Center of Tohoku Institute of Technology. And also I am an appointed professor of Tohoku University, Japan. And this is volunteer activities in IEEE and IEICE of Japan. I am a senior member of IEEE and also WIE MTT SPS member, and also the member of IEICE. And I served as a chair of Sendai WIE and chair of WPT International Subcommittee of IEICE, both from 2020 to 2021, and I just finished the serving as a community member of IEEE Region 10 WIE, and also still a member of the MTTS WIM committee member. And actually this event is sponsored by the MTTS WIM committee. And now from this year, I'm serving as a MTTS Diversity and Inclusion Committee member and also Vice Chair of IEIC of Antenna Propagation Technical Community in Japan. And this is my research area. Actually, I majored on electromagnetic wave engineering, wireless communication, and wireless power transfer, and antenna research. And other information about me, you can look at these linkers. And also this QR code, you can catch it to catch more information about me. Thank you. This is the IoT research members of our university. It's me, and this is a Region 10 WIE committee member, and it's me. This is my small research milestones. From 1992, I researched on P4 antenna for second generation mobile phone. And then I developed a software. It's called V-Color based on momentum method. And in 2006, I focused on the research of mutual coupling in direction of arrival estimation and beamforming. So today I would like to introduce these works mostly. And then I do some research on maximum power transfer efficiency for two-port systems. It's for wireless power transfer, and also I have researched on acceleration algorithm with GPU for electromagnetic simulation software, and recently I have achievement the power transfer efficiency for MIMO WPD systems. So from this, my research areas, I would like to say, so first, it's also the certainly I just focus on pointer technologies now. With the years of research, now I challenge on the system technologies. So today I'd like to introduce and explain the direction of our technology. Now this is the background. So now this is the DOA applications. So actually, there are lots of applications for DOA, and typically it can be used detection of illegal electromagnetic waves, especially in Japan, and has been widely used for mobile communication. As you know, lots of base station, especially LTE. Mobile communication use DOA applications to adaptive beamform the radiation antennas, and also for use disaster prevention systems and so on. Here is a picture of dual loss. It's used for detecting unlicensed or illegal radio stations in Japan. This picture is from the some province of government of Japan. This is array antenna used as dual loss illegal detection system is a 5-element antenna. Now I would like to introduce the DOA estimation method. Here, 6 DOA estimation methods are listed, and also very simple compare their principle, a requirement for array configure, and also need or don't need steering vector and the calculation process. So they are among these methods, the principle usually can be divided into two catalogs. One is using beam searching and another using null searching. So in this report, I just only focused on music method. It's actually use null searching and no special requirement for array configuration. It means it can be used arbitrary array configure, and also need a steering vector. And for the calculation process, it needs to calculate the eigenvalues and also direction searching. So this is a feature of this music methods. Here is the principle of music. Music is the combination of the first characters of multiple signal classification, and it is a highly popular eigenstructure-based DOA estimation method with high resolution, and it was firstly proposed by R.O. Schmidt in 1986. And here is a M element array antenna, and if we have L incident waves, so for each antennas we can obtain the receiving voltages like here, and this is a VR. R is means the superscript R means receiving, and this VR is a vector for it consists of M elements, and matrix RVV is a correlation matrix with size of m times m, and here the operation E means expected value. Usually, the correlation matrix can be divided into two subspaces. One is single subspace, and other is noise subspace. Both can be calculated from their eigenvectors. The signal subspace can be spanned by steer vector, and the other space can be spanned by the noise eigenvalue vectors. So because all the eigenvectors also connected to each other, so finally we can obtain this formulation if the direction arrival is fitted to this theta or phi. So the denominator of this formulation will be 0, and we can obtain the very large PM, the value of PM. It's the spectrum of the direction of arrival. So A is a vector, is an M vector, and it's also be called as mode vector, steer vector, and array manifold, and so on. And N matrix is M time M minus L matrix consists of noise eigenvector. However, the accuracy of DOA estimation is directed greatly by the effect of the mutual coupling between array elements. Therefore, it requires the calibration. Usually, the proportional calibration method has two features. And one is that they calibrate only for received signals, means calibration the voltage of each element antenna. And this calibration matrix C is usually independent of the incident direction of arrival, and it cannot be calibrated exactly for any array with arbitrary element. So here is a universal calibration method is strongly designed. So next I would like to do. Now I would like to introduce the universal steer vector we proposed. The convention steer vector actually it presents the array vector, and each element should be the same and cannot include the effect of the mutual coupling of antenna elements. And our proposed universal steer vector actually it means for the array element pattern, and each element could be different and also include the effect of the mutual coupling. Due to the limitation of the talk time, I will very quickly show you the element pattern with the mutual coupling for this 5-element dipole array antenna. And the distance when d between the element is set to quarter wave length, and this is number 1, number 2, number 3 antenna elements, and because number 4 and number 5 is the same as the number 2 and the number 1, so we don't show here. And here when the distance between array is enhanced to half wavelength, the element pattern like this. If the distance is set to be 1 wavelength, and the each element pattern will be will be similar to each other. And if the distance is enlarged to 10 wavelengths, so almost the element is the same. It's the actually it's the effect of the mutual coupling on element pattern. Now here is called above is USV universal steer vector. Actually, the amplitude and phase are different to each other for each element antenna. And for array vector, it's also a CSV conventional steer vector. Only the phase is different to each other. USV can be calculated by moment method or measured by experiment. Now, today I have no time to explain this very detailed, so I would skip this slide very quickly. Like this is a moment can be calculated very correctly by using moment method. This is finally, I would like to show some estimation results obtained by YUSV. Here is the five element dipole array antenna, and we have three waves from direction like here. This is wave one, this is wave two, and this is wave three. And if we use CSV, we only can obtain this black line. You can see the wave 2, the direction of wave 2 and wave 3 is quite near, so they can the CSV cannot identify very clearly. If we use the USB, we can obtain three direction very clearly. Like for six element dipole, we just change the element distance. This is for half wavelength. It means the mutual coupling is very weak, and this is other case for the very close case when D is set to 0.1 wavelength. So the CS cannot identify these four directions, and however the USB can identify they are very is quite good kind of, and it is also the same case happened to this when D is set to half wavelength. Here is another very amazing examples. We use different elements. Has been used for mobile phone. One is a monopole antenna, and the other is a PFAR antenna, and they share the same ground. So we use two elements can estimate one direction for the incident waves. If we use US, we can instead this way very nice. It's a black line, and if we use C, we cannot identify the DOA because they are very strong mutual coupling. It's an experiment set up for a DOA experiment, but today I have no time to explain them. I will quickly them very quickly. Skip. Okay. Skip. Skip them. Okay. So finally, I would like to introduce you the adaptive beamforming for oriented with mutual coupling. Here is also the six element dipole array, and we have one desired wave from this direction is D means the desired waves, and another three undesired waves. So we use the MMSE minimum mean square error weighting method to obtain these weighting functions, and also use the universal steer vectors. Finally, we can obtain this black line beam forming. As you see, it the beam is directed corrected to the desired wave and make the null to the undesired waves. But if we use CS, it is not so good, especially for the undesired waves. So this is a very nice. So also we have another examples. It's two monopole antennas share the same grounders, and also we have one desired waves and another is undesired waves. If we use we can obtain this beam forming pattern, and the blue dash line is used by CSV, so it can be not makes a beam directed to the desired waves. PFAR antenna is the same result as before. Till now, I have introduced how to use music method to estimate the direction of arrival of radio waves correctly. Actually, if you use n-element array antenna, you can estimate the direction of the n-1 coming radio waves. The problem is a mutual coupling between elements do decrease estimation accuracy. So to overcome this problem, we propose the universal steering vector. And the idea of our approach method does not decrease the coupling between the elements. We only include the coupling correctly. So actually, it can be said DOA estimation with coupling. Thank you for your kind attention.